So we are nearing the end of this module and the overall course slowly. So in fact, at the end of the last class, one of the students asked the question which we will try to answer today. He asked us to, okay, fine, everything, I mean, least square, etc. But how do you know what is the order of the model? That's a very important thing, and in fact, the point to note here is that it's not that there is a it may or may not be true that a so-called true model exists. In many cases, you are maybe you are trying to identify a nonlinear system using a linear model. So in that case, there is no true linear model. There is no true parameter. It's only a question of approximating the system, the nonlinear system behavior under a set of given inputs, I mean kind of input. So therefore, that's why I have used the term model order selection. I am not saying model order determination, because it's not that you can, I mean, nicely solve out that it may or may not be true that you can nicely solve out that the model order is going to be 2. Rather, you have to select whether selection of a model order of 2 serves your purpose well, or selection of 3 is required, or maybe selection of 1 is sufficient. So in general, we would go by the simplest one that works for our purpose. So it's more of a question of what works good enough for my purpose. So in that sense, it is essentially a selection problem, and we will see some broadly, I mean, I will not go into absolute mathematical details of the procedures, because there are certain things, certain basics which will be required, which we have not covered in this course. So therefore, but they are available in very standard material on statistics or on linear algebra. But I hope that the basic approach to the selection problem will be clear. And after you have selected a model, actually, this process is somewhat it's like a chicken and the egg problem. So if you have after you have selected a model, I mean, the proof of the pudding is always in its taste. So I mean, how do you know whether you have selected a proper model? So after you have selected the model order, you have to actually go through the estimation and get some parameters based on those orders, and then see whether your estimation process was really completed, whether you could really fit the data, whether your behavior maps. If it does not map, that is, if you did not get a good taste, then you come back and then you change your model order. So it's not that things can be always determined a priori. Sometimes you can carry out some tests here and there, but in many cases it is essentially an iterative exercise. So you have to select something based on what you feel could be right, then try it out and see whether it's really right. Otherwise, you again start all over with a different model order. So so essentially, there is also a kind of model validation involved. That is, you select a model order, do the estimation, get a model, and then you validate the model. Basically, try to determine whether it's good enough. If you I mean, for doing this, doing the validation, often you have to carry out some tests on residuals. So we will see some of these things. So coming to that, basically the problem is, how to decide the model structure and order that can capture system behavior. And like, I mean, this is a rather qualitative statement, but what it tries to say is that it should be able to capture the system behavior good enough. What do I mean by good enough? For example, if I know that in a regular scenario, for example, suppose if you are trying to model a mechanical structure. Now, obviously, that mechanical structure will perhaps never experience forces of the order of megahertz. That is very unlikely. maybe it will not even experience forces of the order of kilohertz, maybe it will experience only forces in order of hertz, which means that you need to be able to estimate a model which is good enough up to, let us say, 100 hertz. You don't at all bother about how that structure would have behaved if you really excited it at 10 kilohertz. You are not concerned with that because that is not required in the purpose. So this, right? I mean, in fact, things have completely different model structures depending on the use. I mean, I have one of my teachers saying that the model of a transformer, probably this I have said earlier in the course also, that the model of a transformer, I mean a normal power transformer at 50 hertz is completely different from its model at 50 kilohertz. I mean, at 50 kilohertz it is predominantly, it will consist of interturn capacitances, which we completely ignore when we draw an equivalent circuit model of a transformer. So we are talking about system behavior for which the model is going to be built. And so firstly, but in that zone it should be able to model the behavior reasonably well. Again, reasonably well depends on what is the purpose for which you are trying to determine the model. For example, if you are trying to use it for control, then it will happen in many cases that even if you had little modeling uncertainties, the controller will force a response. So the control response, in fact, that is the beauty of feedback control, that it can give you performance even if you don't know the system model very accurately. I mean, especially when you have high gain feedback, then the closed loop transfer function is g by 1 plus gh. So if h is high, it becomes 1 by h almost, because gh is much larger than 1. So the closed loop behavior typically depends on the feedback response rather than the feed forward response. So what it basically says is that even if your model is little inaccurate, if you are using it for control, in many cases it will not matter, right? But maybe if you are using it for prediction or for simulation, it might matter. So that's a very important thing that needs to be remembered here. Now, when shall we say that is, how do we characterize this thing called can capture system behavior? Can capture system behavior means what? So that you can capture, depending on how do you test this, that it can actually capture system behavior. So you will test it typically by looking at prediction error properties. That is what the model says is going to happen and what is actually happening. So I mean, obviously speaking, this has to look at prediction error properties. So you will check for whether the prediction error level is sufficiently low. If it's too high, then there is something wrong with your model. Secondly, in some cases you will get some errors because you are trying to reject noise. So the model prediction and the measurement will be different. In fact, it is good to be different because you are trying to get the process variable before the measurement, right? So you are trying to reject the measurement noise. So while there may be some prediction error, you definitely want that the residual that you are getting is not correlated with the input, because if it is correlated with the input, that means that there is a part of the system dynamics which you are unable to explain using the model. So if you get uncorrelated residuals which are mutually uncorrelated and which are uncorrelated especially with the input, then you know that at least whatever residual you are having, that does not contain any component of input. So you have explained all the input. So these are very important properties of the prediction error that you usually check to know whether you have extracted all juice from the data. Whatever was there which was due to the input, you have extracted into the model. So whatever is remaining is actually useless. That has no connection with the input. And not only that, this you have to do. You have to choose realistic input signal. Otherwise, you can get very different parameters. If you try to estimate a model using DC, I mean DC like thing, and if you put higher frequency component, you can get quite different models. So you have to ensure that the input data with which you have excited the system, which you are using for model building, spans the whole gamut of reasonable behavior which you actually expect when you put the model into use in terms of amplitude as well as frequency. And obviously, to be able to select model structure, you have to use system physics. If in a circuit you know that there are 3 capacitors, then it is very likely that you must start with a third order model, because the physics tells you that there are 3 energy storing elements. So the model order is likely to be 3. Now it may be more than 3 depending on some parasitic effects also, but at least your structural knowledge of that modeling principle will at least make you start from 3. I mean, that will be a good initial guess. So you have to use system process, and you have to use also the knowledge of the measurement process. In many cases it happens that that suppose that the measurement process may have a bias. It may have a DC bias. So if you know that it may have a DC bias, often what you do is you would like to, rather than working on normal data, you may like to work on difference data. That is, you create a different input which will be UK minus 1. Call that the input. See, as far as you are using a linear system model, you are trying to identify whether you are using difference data or whether you are using sum data. It makes, as long as you are doing linear operations on the input, model remains the same, almost, right? So you may like to estimate your model based on difference data. So such knowledges have to be used when you are doing, the model order selection. So now let us see let us get more into specific. So first of all, question is, how do we know whether the model is too simple? There is always a tendency of choosing models which we would always like the simplest model that works. So how do we choose how do you know whether we have got under parameterization? Typical example is that the real model may be a second order thing. We are trying to look for a model which is a first order model. So when do we know how do we know that it won't work? We have to actually go for a second order model. So firstly, that such a thing is actually expected to show high prediction error for some input. If you really need a second order model, now if you can, this you can realize by seeing the Bode plots. Let us say the magnitude plots. For a first order system, it's going to be like this. For a second order system, it will be like this and then like this. Correct? 2 poles. So, but as long as your input is up to this frequency, it's like a first order. At least the asymptotic plot. The true plot is not that. We are just just for simplified argument, we are thinking in terms of the asymptotic plot. So at least up to this can be approximated by a first order system. But the moment you come to this frequency zone, if you try to fit this, you can fit this part, perhaps, in a given range, because around a given point. But as soon as you get this 40 dB per decade slope, this 40 dB per decade slope cannot be obtained by a first order model. Correct? So if you are only considering inputs in this region, then you don't need a second order model. But if you are using inputs in this region, then you do need a second order model, and a first order model will not do. And the difference between the model prediction of the output and the true output will actually show up if you excite it by a frequency in this region, then it will show up. So the prediction error will build up if you give it input of high enough frequency. That is the first thing, that the predicted output from the model and the true measured output will not match. Second thing will show you that if you are having a prediction error level, then you have to experiment, I mean, you don't know what is the model order. So you try with 1, see what's the prediction error level. Then you try with 2. If you find that the prediction error has suddenly dropped, then you know that you should go for 2. On the other hand, if your prediction, if you have a second order system, and if you estimate it using a third order model, what will happen? Some extra pole will appear, both on the numerator and the denominator. But as far as the prediction is concerned, it will be the same. For example, S plus A by S plus A into S plus B, this is a second order model. Actual model is 1 by S plus B. This is a second order model. But if you simulate 1 by S plus B and if you simulate these two, you will get the same output. So because you will get the same output, you will have the same level of prediction error. So in such a case, by increasing your model order, your prediction error will not fall. It will remain roundabout in the same level. So if it does not fall, then you know that you didn't have any gain by actually increasing the model order. Remember that if you are increasing the model order, you are increasing computation. Right? Not only you are increasing computation, you are actually it can be shown that your parameter variance will also increase. That is another analysis. That is, if you take a second order system and if you try to use it using a 10th order model structure, then your variance of the estimate will increase. That is, I mean, if you do it with this data, you will get something. If you use another data, you might get another thing. So that is why you should use the smallest structure which fits the data. So that's the second criterion, that you should try with increasing model structures. At one point you will find that you are not getting any further benefit. Secondly, as I said, that the prediction error would be correlated with the input even in the absence of feedback. If there is feedback, prediction error will naturally be correlated with the input because the input is being computed from the output. So this thing will hold only if there is you are not doing closed loop identification. If you are doing closed loop identification, this thing will not hold. And last thing that will happen is that if you use different data sets, for example, suppose you have used one data set which, let us say, contains frequencies from the order of 0 to 10 hertz, you will get one model. If you take, say, let us say 5 to 20 hertz, you will get a totally different model. But the parameters will start varying too much depending on the inputs, depending on the input property. For example, if you have a nonlinear system, then you can actually linearize it around operating points. Operating points depend on the amplitude of inputs typically. So if you use a very high amplitude input, then you will get a linear model which is around a different operating point. Therefore the linear model will be different. So if you have not modeled it appropriately, then the estimated parameters will actually be dependent on the input signal that you are using. So if you use different input set, you will get different parameters. That is also an indication that your model structure is not good for all that input variation, because it's changing. Right? So these are roughly ways of detecting that a model structure is too simple. It cannot capture the system behavior under the required conditions of the input. So we'll look at some of them a little more in detail. Firstly, obviously, this thing cannot be undermined. Visual inspection of plots and assessment of error levels against model requirement. This is must. You must take plots and you must see with your eyes. That is always important. It should not be discounted in a practical case. And what is meant by assessment of error levels is that one who has knowledge may decide that, okay, even if you have a 0.1 parameter error, this is not going to be of much problem, because after all, what is my accuracy of this or that, or this use of model, 0.1 is okay. So somebody has to decide. So that is a very practical requirement, but we will take a different, we'll look at slightly more mathematical approaches. So here one of the approaches that we uses a kind of technique, mathematical or other statistical technique called hypothesis test. The idea is that you make a statement which is called a hypothesis, and then you try to find out that what is the probability that, see, you have been given some facts which come in the form of data, some values you've got. So you make a statement, and then you try to evaluate that given this set of data to me, which has come from experiments, what is the probability that this statement is true? If that probability falls below a certain level, you say that this hypothesis is not acceptable. So you reject the hypothesis. This is a standard method of statistics. You will find it in any elementary statistics book. This is called hypothesis testing. So here, what is the hypothesis that we are trying to check? So suppose we have two models. One is M1, another is M2. One is of the order N1, another of order N2, and N1 is less than N2. So we have two models, maybe one is first order, another is second order. Now if you estimate them, now you use a first order model structure. If you estimate, you will get some prediction error. Now this prediction error, similarly if you use M2, you will get another prediction error. Now remember that this prediction, you have got one data set, just one data set, one or two or whatever, you have got a finite number of data sets. Now this prediction error that you have got is actually one sample of the actual prediction error as a random variable. Do you realize that? That if you perform 10,000 experiments with the same input, the deterministic input value is same. See how is our output being generated? There is an input and there is some random elements, which is my noise. So this is the random element. If I keep U and do 10,000 different experiments, I will get 10,000 different noise elements, because that is a random variable. If I do an estimation with that, I will get 10,000 different prediction errors. Physical sequences will be different. So they are also random processes. Now we are assuming that let those random processes, one of them have a variance sigma 1, another has a variance sigma 2. Remember that I do not know the value. At best what I can do is, from the given data I can calculate the variance of the prediction error simply by taking square and then summing. Then I will get one sample from the prediction error random process. The random process is a general thing, but based on the data, if I assume one prediction error, if I compute, then I will get one sample from that random process. So the variance of the prediction error that I calculate, it will be a sample, right? So that also may be what we are trying to say is that the prediction error that you have got now for this data set, you may get a different prediction error in a different data set. So you must be aware of its uncertainty as a random variable, and then try to decide, fully keeping in mind that this value that I am using for decision is a random process, is a random variable. So I am trying to, so what is my null hypothesis? Null hypothesis means the basic hypothesis which I want to reject or accept, that the true model structure is M1, and the variance of the prediction error that will happen if I use a model structure of M2, that is sigma 1 and sigma 2 are same, which means that M1 is a sufficient order model. Please try to follow this carefully. Suppose the model was truly M1, a first order model. Then if I choose a first order model structure, I will get some prediction error. If I choose a second order model structure, I will get the same prediction error on an average. Is it not? Because the true model is first order. So again my parameters will match. Now so I am trying to say that I will accept this model to be the true model if these variances are the same. That is the hypothesis I am making. But I don't know these variances. I only know a sample from its random process because I have got one set of data, right? So based on those samples, one sample from this random process, another sample from this random process, I have to make my decision because I cannot conduct 10,000 experiments. So, and what is my alternative hypothesis? That is, if this is rejected, then my alternative hypothesis is that M2 is actually a more general model than M1. So M1 is the class of models described by that structure is actually a subset of the class of models. I mean, a first order models are a subset of second order model structures. All first order models can be described by a second order model structure, but there are second order model structures which cannot be described by first order model structures. Therefore, this is a subset of this. So if this is rejected, then my alternative hypothesis is that M1 is actually a subset of M2, and sigma 1 square, that is the variance that I am getting from M1, is actually greater than that from M2. So there is a possibility of reducing the prediction error. Correct? Now there are some theories which are somewhat complicated, which say that if you have a set of independent Gaussian random variables, say, and if you take their squared sum, then that variable which is their squared sum, it is a function of a number of Gaussian random variables. So it will have a distribution that will not be Gaussian. Gaussian variables, if you just add them, linear operations keeps Gaussian, but if you square them and sum them, it will not remain Gaussian. Firstly, that random variable will not have any negative number, obviously, because it is a squared sum. So such a variable, it can be shown, has a distribution which is called chi-squared distribution. But so this is a very common distribution which is used for, especially for testing Gaussianness of residuals, that whether some random variable is Gaussian or not. Typically people use a chi-squared test, right? So this is also again a standard statistical theory. So here what we are trying to say is that if I compute a variance, what am I doing in variance? I am taking squares of individual prediction errors and then summing. How do you compute variance? Right? So it is not unreasonable to assume that this distribution of the variance is going to be chi-square. Now what you try to, if you accept that the prediction error variance random variable is going to be a chi-square distributed variable. If you accept that, then you can ask that what is the value of chi, that you have got a value of variance, right? Now what is the probability that it has actually come from a chi-square distribution of a given type? And if that probability falls too low, if that probability becomes less than 10%, then you say that no, then this hypothesis, because the chi-square distribution is calculated under that hypothesis. So then this hypothesis led to a chi-square distribution which cannot generate this kind of a variance. When the probability is too low, so my hypothesis is wrong. This is the kind of approach that you take. So what you can do is actually, given a distribution of random, for example, you can easily understand this in the case of Gaussian. Suppose somebody tells you that if you do an experiment, if you pick an object, or if you pick a value or a number, it will come from a distribution of mean 1 and variance 1, right? So you know that the distribution is like this. This is 1. He tells you that it comes from a distribution, that it comes from mean 1 and variance 1. Now you draw something. You got a value 1.69. What is the probability what is the likelihood that this number has come from this distribution? Then you will have to find out that see, if this is 1.69, then the probability that if you draw something from the distribution, the probability that x will be less than equal to 1.69 is the area under this curve. This is the density curve. So for a distribution curve, probability that x is less than or equal to 1.69 is the area under this curve. If the area under this curve becomes 0.95, that means the area under this is 0.05, right? So that means the probability that you will get anything greater or equal to 1.69 is just 5%. So if you got a number 1.69, it's quite unlikely that it has come from this Gaussian process. It's very unlikely. I mean, I'm not using consistent numbers. I do not know for a standard deviation of 1 what is the 95%. Yeah, 95% will be close to 2 sigma kind of thing. So this is the argument. So given a distribution, if you know the distribution, then you can, and if you are given a value, you can determine that what is the probability that value came from this distribution. This you can determine. This is what I am trying to say, simply by calculating the area under the distribution curve. So now you are given a chi-squared distribution, and from the data you got a value of the prediction error variance. So now you have to calculate that what is the probability that this prediction error variance, which I computed from my data, has come from that chi-square distribution. If that probability falls, say, less than some chosen value alpha, which you can choose as 10%, 5%, depends on how sure you want to be, then this alpha is typically called a confidence level. If you want to be 99% confident, then you will set this alpha as 0.01. Okay. So this is the approach, that you first make a hypothesis. Based on the hypothesis, you try to characterize that under this hypothesis some quantity which you are going to test. That quantity is generally called a statistic, not statistics. It is called a statistic. A statistic is a function of which is computed from a random variable and which does not contain any unknown parameter. So if you take variance as the statistic, then you can find out that whether this variance came from this distribution. This is the approach. There are, I mean, I am skipping the mathematical details because that will involve intricacies. Okay, so essentially, basically, I mean, we are just trying to find out whether, basically the same thing. We are trying to find out whether the variance of the error is too large or not. But we are doing it in a mathematical way, and not only that, and keeping in mind that I have just picked one value, so it is a random variable. It could be slightly off. I'm not using a steady threshold, because the threshold has been computed based on the randomness properties of the prediction error process. So the threshold is computed using the fact that you might get a slightly off value when you are choosing a random variable. So this is the principle. Similarly, if you want to compare whether the variance from M1 and the variance of M2, whether variance of the second process is actually variance of the first process. You see, again, you will say that why is it? I mean, that is trivial, because you have already computed this, and you have already computed this. So one will be larger. So what is there? Big thing to test. One will be a larger number. Remember that we are not trying to test that. We have got two distributions. Once this random process, actually I should not have written this. This is strictly speaking wrong. I should have written that whether I can compare sigma 1 and sigma 2. That is, this is a random variable. It has a standard deviation. This is a random variable. It has a standard deviation. That standard deviation is unknown. When I have computed these two, I have just got a sample from this. I've just got a sample from this distribution and a sample from that distribution. So I am trying to find out that if I get this sample from this distribution and this sample from this distribution, then what is the probability that the variance of this distribution is actually greater than the variance of this distribution. So from two samples, I am trying to assess what is the probability that the actual variance is larger. That is the subtlety. So again you can define a variable like this, and in this case it turns out that if you take in this case you see if these are individually chi-square, then their sum will also be chi-square, sum or difference. So, and this is a ratio of two chi-squares. So it turns out, again, theory of statistics, that this kind of ratio of chi-square variables have a distribution which is called an F distribution. These are very well known distributions, F, T, chi-square. So then you have to do, so now you know that if you compute this quantity, then this comes from an F distribution. So again you check that whether under the F distribution property, whether this should actually come out to be what you got. So principle is the same. You compute a statistic, find its property, find the property of its distribution, and then check whether this value that you got, how probability is to get it from that distribution. The same thing again. So then you can again test whether what is the probability that this is greater than this. If this is greater than this, then you reject the hypothesis, saying that it cannot be so large. With alpha level of confidence, you can say that it cannot be so large. So this is a way of checking, because variances are why you have to do so much, because you have to always remember that if you are seeing a plot, you are seeing a plot for only one data set. What is the guarantee that if you took another data set, you would not see a different plot? So you cannot, that plot is not certain. You have to always be aware of its uncertainty as a random process. Next is correlation tests on prediction error. So why? Because we know that prediction errors are supposed to be white. If you have taken out all information related to input, and assuming that these are all assumptions that noise processes are generally of white nature and they are not correlated with the input. If you have been able to explain the whole input, then this will also be uncorrelated with itself. If the original noise is uncorrelated with itself, which was the assumption. Remember that if your measurement process includes a DC term, will it happen? It will never happen. So which means that, but if your measurement process includes a DC term, then what will you do? Then what you should do is that in your model you should contain a DC term. Then you should write that yt is equal to minus a yk minus 1t plus b uk minus 1 not t yk uk minus 1 plus some c. If you think that your output measurements contain a DC, then you should, in your model structure, you should include a DC. And then say that my data vector should be minus yk minus 1, uk minus 1 and 1. And my parameter vector will be a, b and c. If you think that you have a DC bias in your measurement, you should model that bias. Because if you don't model that bias, this property will never be satisfied. Okay? So it is expected that you have the regular properties you have all modeled. Then whatever will be remaining should be uncorrelated. That is the expectation. So again, remember that if you compute this from your data, you will get a sample. Basic principle is the same. You want to test for whiteness of this. That is for only for r epsilon tau equal to 0, you will get some correlation. If tau is anything greater than 0, the correlation should fall sharply. Okay, then it is uncorrelated. So again, you have to test those things, that you have to form a statistic and then check whether this quantity is chi-square distributed. because again you are checking for correlation, which is like a product of variables. So again the distribution is going to be chi-square. So here you are checking. So you see that the same kind of test so what are you guessing? That you are what are the steps that depending on the property that you want to check, you have to formulate a suitable statistic. In this case, this is the statistic, and then you have to choose it in such a manner that it gives you a known kind of distribution. For example, in this case it gives a chi-square distribution, and then check the value against the properties of that distribution using a hypothesis test, right? So just wanted to explain the principle. Similarly, you can say this test whether the residuals are autocorrelated or not, epsilon. Similarly, you could test whether the residuals are correlated with the input, in which case you have to test for cross correlation. So you could also formulate something like this, epsilon k uk minus tau, and then again formulate a suitable statistic such that this will follow a particular distribution and then check for hypothesis testing. So this is a general approach which is followed in checking, very much used in model order checking. Then the other approach, which is simpler conceptually, is to do structural tests on matrices. Suppose you have a data vector, right? So you have minus yk minus 1, say minus y1 u1, minus y2 u2, and so on. This is your data vector phi, right? This is your data vector for a first order model. Similarly, you could have a data vector for a second order model. So suppose the system is truly first order. Now I am assuming that the system is exactly like this, and you have chosen a model structure which is like this, which is second order. You have taken two past inputs. Now obviously you know that yk minus 1 is a function of yk minus 2 and uk minus 2, because the system is like that. The true data which you are putting in the matrix is there yk minus 1 will be equal to minus a yk minus 2 plus b uk minus 2. So this row and this row are going to be correlated, linearly dependent. If you take this row multiply by a, if you take this row multiply by b, you will get this row. Row, not row, column, right? So therefore the rank of this matrix will fall. In general, what is the rank of this matrix? The rank of a matrix of dimension m by n is minimum of m and n, provided when maximum it can be is minimum of m or n. So generally the number of data points is much larger than the number of the number of columns. So maybe you have 1000 rows and you have only 3 columns. So that kind of difference. So therefore the rank is always determined by the number of columns, theoretically, practically rather. So what will happen is that if now some columns become linearly dependent on other columns, the rank of this matrix will be less than the number of columns. So that immediately shows that you are now getting a rank deficient matrix. So that means that so many columns are not needed. Some columns can be generated from earlier columns. So you don't need to complicate your model structure. Now the only catch is that because of noise, exact singularity cannot be obtained, because all these exactly this will not match, even in the measurement, because of noise. So therefore exact singularity you will never get. Therefore you should try other things. So singularity, rank testing of a matrix is actually a very numerically susceptible thing. You have little errors here and there, you will not get rank as, you may still get a rank. You may get a higher rank, though the matrix is singular. So in such cases what you should do is, you can do two things. Let me discuss the first one, second one first, because that is simple. if you consider, if you constructed a determinant of, actually this should not be phi, this should be phi transpose phi. Phi is a non-square matrix, it cannot have a determinant. So if you take the, now if you have a matrix, this is phi and this is phi transpose. So therefore the overall matrix will be, now rather this is phi, so this is phi transpose, so you are having phi transpose phi, so it will be if this is m into n phi, then phi transpose phi will be n into n. Now because the rank of this is less than n, so therefore phi transpose phi will not have n into n full rank. So therefore phi transpose phi will tend to become singular. It will come very close to singularity. Coming close to singularity means what? Determinant coming close to 0. When does the matrix become singular? When its determinant is 0. So if you start expanding the phi matrix, at some point suddenly the determinant will come close to 0. So now if you compute checking, let us say first have 2 columns, okay, first order model. Compute phi transpose phi, compute determinant, you get some value. Then you choose model order as 2, so you choose a phi with 4 columns. Immediately what will happen is that the determinant of phi transpose phi with 4 columns will sharply fall. It may not be exactly 0, but it will sharply fall because it will become very close to singular. So immediately that will show on this ratio. So the idea is that you go on increasing the model order, every time compute determinant of phi transpose phi and check when the determinant is falling rather sharply. Stop at that level, don't increase. That's a simple numerical approach. Similarly, you could do singular value decomposition rather than typical way of detecting whether a matrix is very close to singularity, may not be exactly singular. If then is to compute singular values. So you take a matrix and you do a singular value decomposition, which is a very standard numerical practice. Basically break it up into U as V transpose. Then this matrix is actually diagonal and its elements are called singular values. If the matrix is close to singular, then what will happen is that maybe suppose the matrix is 5 by 5, if it has 3 singular values which are nice and good, maybe 10, 15, and suddenly the 4th and 5th become 0.01 and 0.02, then you know that the rank of the real rank of the matrix is 3. It's not 5. So you check the singular values and you reject the rows corresponding to the ones which has very low singular values. These are numerical procedures. So you can find a good idea of the order by looking at the data matrix properties. That's what I'm trying to get at. So by taking the matrix phi and then computing either a determinant ratio or identifying the singular values of that matrix, you can get a very good idea of what is the likely order. So we are coming close to the end. Yeah, this is another point that I tried to make without becoming too mathematical, is that if you, for example, suppose this is the old point that I am trying to make, that if you have a second order transfer function, if you are using an input spectrum which is here, then you will probably get a first order model like this. If you choose an input spectrum which is here, then you will get a first order model maybe like this. And if you choose it here, then it will just try to match it as close as possible around this zone. It cannot anyway approximate 40 dB per decade, this thing. So it will be somewhere like this. So what I am trying to say is that this, because the true system is second order, if you are using a lower order model, then the parameters that you will be getting will be highly dependent on the kind of inputs that you choose. But if you had obtained a second order model, if you have taken a second order model structure, whatever input you give, you are likely to get this form. The parameters will not change, right? So that is also that could also serve as an indicator that your model structure is not same. I mean, every time it is trying to match some property somewhere, so it is moving. Since it has there is a big thing, system is big and you are using a small torchlight to actually know what the system is. So it is now focusing on this, now focusing on that. It cannot show you the whole thing. It is showing only that part which you are exciting. Right? So these are, I mean, I am giving very qualitative explanations because the mathematics involved with this is quite substantial. I don't want to get into this, but I want you to get the idea. So while concluding, I would just like to say that finally, if you really want to do it in practice, you will necessarily have to iterate. You have to, this is a trial and error procedure. Don't think that you will get the data and put it into a nice algorithm and then it will say second order, second order. Nothing like that is going to happen. You have to do multiple tests. You may have to do multiple tests. You may have to iterate. You first time think it's second order, fire another test, it might say that no, it's not second order, it's first order. And finally, you may have to decide based on judgment. Typical example is, suppose you find that most of the singular values are, I mean, you know that based on computing time, you can at most choose a fifth order model. 4 of the singular values are nice and strong. The other 2 are lower, but they are of the same order. Which one do you reject? So finally, you will have to adopt judgment. You may not always get a nice clear answer, which always happens in all engineering exercises. Mathematics is not a substitute for that, not yet. It helps, but not always. So that's all. In the next class we will discuss there are various practical aspects which you must follow if you really want to identify a model in practice, right from choosing your sensors to doing signal conditioning to choosing ADCs, all sorts of things. So we'll discuss on that in the next class. Thank you very much.